Welcome to BE 110 Introduction to Biomechanics. Biomechanics is mechanics applied to biology. Now, mechanics and biology are two very large fields of study, which means that biomechanics includes a highly varied variety of subjects and areas of study. They range from sports mechanics, analysis of gait. Hospitals usually have gait labs for analyzing patients with cerebral palsy and stroke. Rehabilitation. Other areas, non-medical areas like the growth of plants, the flight of birds, the swimming of marine organisms. There are also many applications in the bioengineering design of medical devices such as surgical devices, prostheses. This includes biomaterials, particularly the mechanical properties of the biomaterials rather than the synthesis and manufacture of them. There are investigators who work on the mechanics of invertebrates. Cell mechanics is a big area of basic science, and tissue mechanics and wound healing and organ mechanics are all other areas in which biomechanics has made and continues to make significant contributions. So in this course sequence, our main focus is going to be on the application of continuum mechanics applied to problems in mammalian physiology. This has been a major focus of our program at UCSD since its inception, and as Y.C. Fung described this, our objective is to solve problems in physiology with mathematical accuracy. Before we can learn continuum mechanics, we have to learn some basic mechanics. So let me start by reviewing some of the major branches of mechanics so we can understand the relationships. So mechanics can be divided into the mechanics of rigid bodies, where we're not concerned with the ability of the material to change shape or flow, and the mechanics of deformable and flowing continuous media. So this side is the focus of continuum mechanics, whereas the mechanics of rigid bodies includes the studies of statics and dynamics. Then within dynamics, we have kinematics, which refers to the motions of systems of particles and bodies, and kinetics, which refers to the forces that are involved in producing those motions. In continuum mechanics, we can solve problems in solid mechanics or in fluid mechanics. And frequently in biomechanics, we have materials that have both solid and fluid properties. Within solid mechanics, there are additional specialties such as elasticity and plasticity, finite elasticity, and within fluid mechanics, there tend to be specialized study of particular types of fluid flows, such as compressible flows or incompressible flows, or turbulent or laminar flows. So statics is concerned with rigid bodies or systems of rigid bodies, such as structures, where there are no accelerations and the body is therefore said to be in static equilibrium. The potential of these bodies to deform or change shape under load or to flow is not taken into account. That's what we mean by rigid. Therefore, the properties of the particular material are not considered, just how the forces get distributed between the components of the body based on the laws of mechanics and under the assumption that the body is in equilibrium. In dynamics, we're still limited to rigid bodies or systems of rigid bodies, but now accelerations are included, and therefore the role of inertial forces come into play. So inertial forces are the forces associated with accelerating masses, i.e. the forces that you calculate using F equals ma. And bodies that are accelerating and have inertial forces are not in static equilibrium. Kinematics refers to the motion of particles or points within a body, and kinetics refers to the relationship between the motions and the forces that produce them. In contrast to statics and dynamics, which are concerned with rigid bodies and only require Newton's laws to solve problems, continuum mechanics is concerned with the mechanical behavior of deforming solids and flowing fluids on a scale in which their physical properties, such as mass, momentum, and energy, can be defined by continuous or at least piecewise continuous functions. So what do we mean by scale here? So what we mean is that the scale of interest of the problem is large compared with the characteristic dimension of the discrete components of the material. Now, what those are depends on the material. For example, in a tissue, it could be the size of the cells. In cells, it could be the size of the protein complexes. It's in a bucket of sand, it's the size of the grains of sand. So the scale is determined by the composition of the material and the relative discreteness of the material. And we can approximate those materials that actually have discrete constituents as being continuous when the scale is sufficiently larger than that individual discrete scale. And as a result, in a material continuum, we can define the densities of mass or momentum or energy or other physical quantities at any point in space, and then represent those densities as continuous functions in space. So for example, mass is not a property of a point, but density rho is the limit as the volume delta V tends to 0 of delta M over delta V, where delta M is the mass contained within delta V. So although a point doesn't have mass, it can have mass density, and we can have a continuous function. Now, important quantities in mechanics include scalar quantities, such as mass and energy and density. Vector quantities, including force, displacement, velocity, acceleration, moment, and momentum. And these are the quantities that we'll use in statics and dynamics. And in continuum mechanics, there are additional important physical quantities which are tensors. And a tensor is to a matrix, square matrix, what a vector is to a column matrix. And properties that are tensors in mechanics that are important are stress, strain, and rate of deformation, among others. So in the same way that a vector, which is a physical quantity, can have components in a particular frame of reference that are represented in a column matrix, a tensor is a physical quantity, one defined by two vectors, if you like, whose components can be represented by the contents of a square 3x3 matrix. So the distinction between the tensor and the matrix is the same as the distinction between the vector and the column matrix. If you think about it, a vector being a physical quantity, the components of the column matrix that describe it depend on your choice of coordinate system. And if you change the coordinate system, but the vector is a physical quantity, then the components of the same vector must be different in a different coordinate system. And that's exactly the same for a tensor. If the tensor is a physical quantity that's represented by a matrix, if you change your coordinate frame with which you use to describe it, because it's a fixed physical quantity, it'll have different components. This idea really comes about from the idea or concept of an observer invariance. If something is a physical quantity, then it can't depend on who's looking at it. And if I use one frame of reference and you use another frame of reference, we're going to, and we both look at the same physical quantity, we would come up with different components. And so there must be a relationship between the components I measured and the components you measured, and that relationship purely has to do with the difference between my frame of reference and yours. So this is the important distinction between a tensor and a matrix, namely that the tensor is that physical object. Now, the rules of mechanics are the conservation laws for conservation of mass, momentum, and energy. And the starting point for coming up with these rules are Newton's laws of motion. In statics and dynamics, Newton's laws are all that we need. They give us a set of governing ordinary differential equations that simplify to algebraic equations, or the special case of static equilibrium. And we can derive, and will next time derive, these governing ordinary differential equations from Newton's first, second, and third laws. And these equations of motion give us the conservation of momentum, and the conservation of momentum idea can be extended to a continuum, as can conservation of mass and energy, and then we have the equations for continuum mechanics. But in statics and dynamics, the mechanical properties of the material don't come into the problem. All we need is the distributions of forces and the geometry of the body, which we frequently reduce just to points such as centers of mass. We don't need to know the physical properties of the body because we consider them to be rigid. Whereas in continuum mechanics, Newton's laws, instead of being a system of ordinary differential equations, become a system of partial differential equations, as do the conservation of mass and energy. Because now we are enforcing these conservation laws at every point in the material continuum, not just for a discrete set of points or lumped masses. Now, in addition to these conservation laws, in continuum mechanics, we also need equations that describe the mechanical properties of the particular solid or fluid we are trying to study. These equations are called the constitutive laws because they represent the contributions of the constituents of the material. And they give us the stress in the material as a function of some measure of the shape change or flow, such as the strain or the rate of deformation, or both. For example, in an elastic material, the stress in an elastic solid is a function of the strain in the elastic solid. In a viscous fluid, stress is a function of the strain rate or rate of deformation in the flowing fluid. And in a viscoelastic material, the stress is actually a function of both the strain and the strain rate. Now, the constitutive law must generally be determined by experimental testing. It is constrained by physical principles such as conservation of energy and mass, but only in the most idealized of situations can it be derived from first principles. In practice, particularly for real biological materials, the only way to determine the constitutive law is to make measurements of the physical properties of the material of interest. Now that we know the governing equations of continuum mechanics, namely the conservation law and the constitutive law, we can actually outline all four elements of a problem in continuum mechanics, the four things you need in order to get an answer. First, you need the geometry and some information about the structure of the body of interest. Secondly, you need the boundary conditions, and if it's a time-varying problem, initial conditions. Third, we need the conservation laws, the conservation of mass, momentum, and energy, which are universal for all material continua. And finally, we need the constitutive law, which is specific to the particular material that we're studying. So let's look at biomechanics, particularly the biomechanics that we're aiming to focus on at the interface between continuum mechanics and physiology. On the left, let's consider the components of the continuum mechanics problem. And on the right, let's look at the analog in physiology. So in continuum mechanics, we have geometry and structure. Well, in physiology, usually the first thing you learn about the physiological system is about its anatomy and morphology. You can't understand how an organ or tissue works until you know about its structure. The boundary conditions in a mechanics problem correspond to the environmental influences acting on the tissue or organ, and as you know, that's a big part of physiology. Now, the conservation laws are analogous to the biological principles that we learn about in physiology, such as homeostasis. For example, conservation of mass goes along with mass transport and growth. In fact, many important physics laws, like Fick's law, were actually first described by physiologists. Conservation of energy, as you know, in physiology, we're interested in energetics and metabolism. And then conservation of momentum, we're interested in physiology frequently in motions and flows and the homeostasis and equilibrium of tissues. And finally, we have the constitutive equations in continuum mechanics. Well, they correspond to structure-function relations for mechanical behavior of tissues and organs in physiology. So you can see there's a very natural relationship between continuum mechanics and physiology, and this is one of the reasons that the continuum mechanics approach to biomechanics has been so powerful and successful. So in summary, continuum mechanics provides a mathematical framework that allows us to integrate the structure of cells and tissues into the mechanical function of the whole organ or organ system. And so that's the goal of this biomechanics course sequence, and the goal of our course is to give you the preliminaries in statics, dynamics, and continuum mechanics that you can start to take on these interesting problems in biomechanics. Next time, we'll introduce some of the physical properties of mechanics and review their definitions, and then we'll go on to derive equations describing Newton's laws of mechanics.